So here we are kind of at the beginning of Unit 3, which is our test on advanced integration techniques. If you have the time, I strongly encourage you to look at your textbook. Within WebAssign, you can find it. Go to section 8.1. I think your author did a fantastic job of starting off this chapter with, hey, here's everything that you've learned about integration right now. Because all of that is still fair game. Your author is very good at, when you're learning these advanced techniques, to throw in the old school basic integrals as well. So you have to be on your toes. You have to know what you know up until this point. Basic integration, use substitution, be flexible, and then realize, wait, none of that works. Let me try something fancier and more advanced. So if you have the time to set aside before you really get into this section, pause the video, go to 8.1. I have some suggested problems from the textbook. They're not worth credit, of course, but it's good to take a look at those to see, like, even just look them over. Like, am I okay with these? Maybe you don't have to do every single problem, but you should certainly think about it, if not do them all. So anyway, here's my best quick version of what 8.1 sort of has. Not a lot, this is very basic, but just the structure of what you see. So to do problem number 1, obviously this should not bother anybody. This is your basic power rule integral, right? So if I just kind of look at that, well, that's x to the first, and you know your power rule for integration is add 1 to the exponent, divide by your new exponent, slap on that plus c for that constant integration, and you're all set. So nothing horrible, nothing to see here, nothing fancy, nothing advanced. Same thing with problem number 2. You have to know this, what the integral of cosine is. I know you guys do know that. And so that is just sine. Nothing terrible. This is a basic integration rule that certainly is always on the table. When you move on to problem number 3, nobody's annoyed with that coefficient of 3. Of course, you're allowed to pull out coefficients from an integral and deal with the functions of x inside. What you can't do is pull an x variable out of an integral. That is illegal. That's going to get you into a lot of trouble, and I'd have to stop looking at your work at that point because it's terrible. Okay, but I can take a coefficient out, no problem. So I just have a 3, and then, the integral of cosine is sine, again, constant of integration, because all of these are indefinite integrals, and keep moving, right? And in Calc 1 and a little bit in Unit 1 in this course, we revisited the idea of use substitution, which is what you need to employ here on problem number 4. We need to make this look just as nice as problem number 2. And a lot of you might just look at it and dream it up, like, oh, I need a coefficient in here. Totally great. I come at this with a use substitution, and I think about it of your best first choice of u is something inside a composite function. So that 3x is sitting inside that cosine. It would be inappropriate on this problem to say, oh, I'll just take the 3 and dump it out in front. You cannot do that. That is illegal. The 3 is not a coefficient. It's actually embedded in that cosine function. So I can't do it that way. But I can do a basic u substitution, which you're going to have to employ a lot in this unit. We're going to learn some fancier things for sure, but all this old stuff is certainly on the table. I end up doing the follow through here to figure out like where I'm headed, and I reimagine this integral, right? I say, so I had this integral of cosine, right? I just replaced that me inside with a u, and then I'm going to replace dx with du over 3. So here's where now it becomes legal. You've correctly addressed the 3. You are allowed now to take that 3 out. Notice it's in the denominator. So you can pull it outside the integral as a 1/3 coefficient. That's appropriate here. And really, you've just made this integral look just as nice as problem number 2, because you know the integral of cosine of u is sine of u. The only thing you have left to work on is you have to switch back to the x variable. If your problem was presented in the x variable, then your answer should be presented in the x variable, and so we'll do that. Again, don't forget that constant of integration, super important. Now, The problem area here happens to be problem number 5. You have never seen an integral like this before because you did not have the skills. Your Calc 1 instructor would never have given you this integral because it was beyond the scope of the course, right? And I didn't give it to you in Unit 1 because there really is no other way of addressing this with the skills that you have. You know, it's certainly not a basic integral. You've got a polynomial multiplying a trigonometric function. That's more advanced. You also can't really employ that method of use substitution, because if you just kind of think about it off the top of your head, if you say, hey, let me let u equal 3x, I mean, you can try and all, but it's really not going to work out. When you go through these substitutions and say, okay, I'll let 3x be u, I know I still have that cosine, I'll figure that out later. Maybe that substitution for dx will come through for me. It does not. You have a glaring problem here of this use substitution did not work because you have a function of x that you can't pull out of the integral. You can't reimagine and rewrite it based on your substitution. You are really stuck. So when this happens to you, you have to, just, nope, not happening. Use substitution fails, and that's okay. And I've done a lot of integrals in my life, and I come up in this situation, no problem. I'll choose something else then, right? So you can say, well, how about I come at this and say, what if I let u equal cosine? Well, good idea, not a bad idea, right? What are you going to do? You can go ahead and take your derivative. You can go ahead and do your follow through and see what happens. Maybe this switcheroo will make your life easier. You left the 3x alone. This time you let the cosine of x be u. And now you're replacing dx with du over sine x. You have a double problem here that not only do you have a trig function left hanging out, granted in the denominator, you cannot pull that out of the integral, that is a function of x. You have another x variable over here. This is a serious problem that we cannot solve with the techniques that we have learned up until this point. So you had some good ideas. They just fail. But my number one suggestion with any integral is you try your basic structures first. Try a basic integration rule. That doesn't work, move on to a u substitution. See if that works. Sometimes that you'll be done. And if you've thought about those two options and those don't work, well, then we'll move on to the more advanced techniques. And one of those more advanced techniques is integration by parts. So I'm sure your Calc 1 instructor made a big deal that u substitution, that whole method of integration, actually kind of fell out of the chain rule for differentiation. You can kind of see that where we're doing inside versus outside. That's what the chain rule handles, composite functions. On the flip side here, now we're going to start talking about integration by parts, which really came out of the product rule for differentiation. So I'm just going to talk this out a little bit and see where we get with this, right? So let's say, I'm back in derivative land, right? I have this expression u times v. And I want to come in here and take the derivative. I want to take the derivative. These are two functions with respect to x. I want to take the derivative. No problem. Let's actually write out what the product rule says. You all know it. Order doesn't matter on product rule because it's addition, so it doesn't matter. I usually do first times the derivative of the second plus the second times the derivative of the first. Okay, that's what your product rule is. I know I'm writing it in a weird way with these primes, but you probably used it with f and g instead of u and v. I'm trying to be really mindful of making the u's very curvy and the v's very pointy. I'm just going to change the notation slightly. Instead of v prime, I'm going to call that dv. And instead of u prime, I'm going to call that du. All right, so this is still, the derivative of u times v. Now, we know that if you have this derivative rule here, if I were to integrate it, then you'd get back to u times v. So let me tell you what I mean here. I want to come in here and say, look, what if I just threw an integral around this? What if I did that, right? What if I just kind of left this crazy statement here? this should equal, no joke here, this should equal u times v. Of course, like a constant of integration would come into play there as well, right? Let me just make that capitalized, right? So you know that if you integrate your derivative, you would get the original function back, right? So we're just kind of playing around with this idea. You know, this straight up is your product rule for differentiation. And we're sort of saying, hey, but what if I take that answer, that derivative answer, and I integrate it? What would I end up with? Well, you'd end up with that original crazy expression of x, u times v. Of course, there might be some number, that constant of integration, that you may have lost in that process of differentiation. So what integration by parts with is it actually just sort of looks at this and wiggles it around a little bit. I know that sounds very immature, but essentially that's what I'm going to do. What I'm going to do is now just come at it like this, like right from this line, and say, okay, what if I just mess around with this? We know that when you have an integral and it's separated by a plus or a minus sign, those are separate terms, and you can certainly work on those integrals separately. You don't have to see it as one colossal problem. You can break it up into smaller pieces, which often is helpful. Okay, so I'm just sort of breaking that down. And then, you know, I do have that constant of integration. I'm going to kind of ignore it for a minute for right now. But all I'm going to do here is wiggle this statement around. Okay, I am going to come in here and I'm just going to take this guy right here and shoot it over to the other side of this equality statement. So what does that get me? Well, basically I'm isolating the u and the dv, and I'm going to say, hey, this is equivalent to the integral of v du. Let me put it in the right order here. What is it? Oops. It's u times v, and then, of course, when I move this over to the other side, it is negative the integral of v du. Now notice I'm kind of leaving off that constant of integration. Let's just talk about this for a second. This 100% is integration by parts. This is what everybody knows as integration by parts. And I like to think about it as integration by parts for a couple of reasons. For one reason, you're breaking up your integral. I just want this to look prettier. You're breaking up your integral into parts. You're going to make part of your integrand, you're going to call u, and the other part you're going to call dv. So you break it up into parts, and you see, like, hey, can I take the derivative of the u? Is that easy and manageable to do? The part that I call dv, could I integrate it and actually understand what that function v is? Could I do that, relatively in a manageable way? Then you would get part of your antiderivative in a flash. You would get part of your antiderivative is u times v. That's part of your answer. And then you have this other part where you're hoping this integral is like, I don't want to say easy, but you hope it's like a quick thing to do. You have part of your antiderivative here, and then part that you still have to work on. So it's integration by parts, right? And so you see this very vague and very open statement down here of like, here's my strategy of integration by parts. Step 1. You tried a basic integral, it didn't work. Step 2, you tried u substitution, it didn't work. Now you actually consider integration by parts and you try to let u be something that's easy to differentiate. If you're going to set u to be something, you want to make sure that you can relatively manageably find its derivative. And whatever you set dv to be, you want to make sure that when you integrate dv, then you would actually get a good expression for v. So you want dv to be something that's relatively easy to integrate, and you want u to be something that is relatively easy to take the derivative. Again, let me come out here and make these as pointy and curvy as possible. Okay, so we are going to attack that problem number 5 again. And you can try, sometimes you're not going to get it right with what's u and what's dv. No problem, totally fine, and I'll show you how you know you'd be going in the wrong direction, okay? So let's come at this and say, all right, sometimes I actually look at this one first. I try to find the most complicated part of the integrand that I think I know the antiderivative of pretty quickly. I actually start with that. So that means here, that cosine x, right? And I'm going to throw this in here too. That whole thing, I'm going to say that that is dv. It's trig function. Nobody really likes trig. I get that. I'm going to let the dv part be the cosine x dx. And the reason I'm going to do that is because I can integrate that, and that will get me v. And I know that integral really well. We already talked about that on the last page. It's sine. Now, I'm not going to put a plus c here because we're kind of working with this integration by parts. So what that means is the other part of the integral that I did not touch, the 3x, that has to be u. You have no other option. Good news for you is that's pretty easy to take the derivative of. That's just 3, and then I just slap a dx on there, right? So here's what I'm going to do. I'm going to transform this integral. We already proved that u substitution was not the way to go on the first page, which is why I moved into integration by parts. And I am going to morph this over. Remember, integration by parts basically means I already set the u and the dv. My answer to this is going to be u times v minus the integral of v du. Now, what does that mean for us right here? Well, let's think about it, right? U times v is multiplying these guys together. 3x sine x. That's part of your antiderivative. Done. Like, that's part of it. Now I'm going to come over here and say, oh, I hope this is easy to do. Let's integrate v du. Well, here's v, and here's du. So I'm integrating sine x times 3 dx. This is not bad because you know what? That 3 can actually even come out of the integral if I want, right? Like this is a very manageable integral to work on. That I can go ahead and do that. Let's actually take that 3 out, right? That's legal. It's just a coefficient. There's no x in there. And then I'm going to work on that antiderivative. The antiderivative of sine is negative cosine. That's not horrible. I'm going to slap a plus c on it now because I kind of worked on that. And then what else do I have going on? Well, everything else that I had said. I've got the 3 multiplying that. I've got the 3x sine x in front. And so all I have to do is clean this up. Here is my antiderivative for problem number 5. It is more advanced. It is fancier. You have arrived at your solution, right? And so it is more cumbersome. It is more than u substitution, right? So that's why it's in chapter 8. This is where we get the more advanced techniques. And really, this is showing your work for integration by parts. You know, what did you let u equal? What did you let dv equal? That's how you broke up your integrands. And how did those pieces fall together? All right, now, let me just take a minute here and talk about how do you know this is right? Can you check your work? Of course you can, because what you can do is just take the derivative. So let's just do that for a second. Let's check our work by taking the derivative of that final answer. So what would that mean? Well, I'd need a product rule, right? So I'd have, let's see, 3x and sine. 3x, the derivative of sine is cosine. Then I'll add to that the derivative of 3x is 3, leave the second guy alone. The derivative of cosine is negative sine, right? And the derivative of that constant of integration would be 0. So guess what you have? These guys cancel out. Yes, if you take the derivative of your integral, you ended up with the original function that you had started with. So this should definitely make you feel better. You certainly do not have to check your work. I'm just saying, if you feel uncomfortable or you feel like, I don't know, did I make a mistake? You always have a strategy to handle it, okay? So this is your correct integral for the integral of 3x times cosine of x. Okay, again, you don't have to do any of this checking work. I could just leave that totally off the page here. But if you wanted a strategy of like, how do I know I'm right? You could certainly take the derivative.